Okay, so we're almost done with the semester. Last 2 days of classes. Um, and if you look at the calendar, we're pretty behind on where I wanted to be. I would have loved to have gotten to some more of the applications. But sometimes that happens. Classes just don't go exactly how we thought that they would run. So today we're going to be talking a little bit about boundary value solutions here. Um, and my hope is um, sort of where we can end up with is maybe a conversation about turbulences. And I think most people are interested in understanding how planes fly. So we unfortunately don't have enough time to do the entirety of how planes fly, but we can just start by saying, yes, it's perfectly fine to think about it in the context of Bernoulli's equation, as long as you think about it as that's the first order approximation. Because we want to think about what Bernoulli's equation says. Bernoulli's equation says a couple things. One, it says that you have some ideal fluid and that the fluid itself is irrotational and viscous free. And we know that that is certainly not the case for planes, right? Because planes themselves, they travel in the air, and the air, of course, has viscosity. And when we talk about the air having viscosity, we think about it in this context. So let me see if I can pull this down real quick just before we get into this. Okay. So this is still an irrotational flow. You have U at infinity, means that you have totally parallel lines coming in from the left-hand side of this image. That's the same, of course, to air being still and the wing flying to the left, right? So from the reference frame of the wing, these are laminar flows. That is to say, they arrive in layers. And the question is, how does this laminar flow behave in the presence of an object? Okay. So here we have an object. We don't really care what the shape is right now. But what you'll notice is that there is this thing that's called delta, right? We call it the boundary layer. And this is a region in which the transition from this so-called laminar flow, the steady laminar flow here, goes towards zero. And you can kind of see that from the velocity profile here, u of x. So u of x, where x is vertical. Far away, we need to be able to ignore the fact that there's a wing there. Because the presence of the wing here does not communicate infinitely far away that there is a wing, right? So instead, there is a small region, a small transition region that is basically incorporated by the fact that there's a boundary layer, and then above that, a transition back to the excuse me, to the, it's not quite a boundary condition, but it's a boundary condition when you think about it as x going towards infinity, right? So it's not a boundary, but it's how we think about the problem moving away. So in that process, then you have the velocity profile. It needs to go to zero exactly at the surface, right? And smoothly, it heads towards some u of x, and it can take any shape that it wants in the middle. And the geometry of the object itself, the parameters of the flow, whether they are pressure gradients, we saw when we had that tube that that is going to set how that profile occurs or develops within a boundary layer. Okay. And the width of that boundary layer, delta, or the height of that boundary layer, is going to change as a function of various parameters here. Cool? Questions, comments, concerns? Okay, so here we're talking basically about chapter 10. And when we talk about chapters, so we already, I mean, I would love to do a lot more in laminar flow. But I'm just gonna basically give you the highlights since we don't have that much time. And we're gonna mostly tie this into its relationship with turbulence. So for a thin boundary layer, I'm gonna write here on the right-hand side the steady momentum equation. So steady means, of course, that du dt is 0. So we can say something like u du dx plus v du dy is equal to -1 over rho dp dx plus nu del squared u del x squared plus del squared u del y squared. Right, for the u component. Right? So one thing that we want to do is we want to think about the different terms here. So on the left-hand side, this is the advective terms, right? Here we have some pressure terms. And you have the viscous term. Okay. So we want to think about how do we compare the strength of these terms? What would we do to compare the relative strength or order of these terms?
Make some assumption about something.
Okay, how would we do that?
Well, you said we're gonna ignore viscosity, right?
Are we?
Or no? You said non-rotational or something else?
I said when we do Bernoulli's, we do ignore viscosity.
Okay.
So if we want to take that next step, if we want to be a little bit more advanced than Bernoulli's, we in fact have to add viscosity. Because this image that you have on the right, if there's no viscosity, what does it look like?
It's just all smooth, like the same shape as that.
Yeah, well, so it goes like this, right? And these layers, they're going to be able to touch. And you're able to have flow move across the boundary. Right? So remember, viscosity is the one that is transferring the momentum as a function of height. Right? If the flow goes in this way, then it drags in the other direction. And similarly, because it cannot flow here, that drags this back down to 0. Right? Okay, so we need this term. But you have the right kind of idea. You're looking at the terms, you're trying to figure out how we can make this more understandable. And what you should be thinking about first is what is the size of the relative terms? So if I look here, the advective term goes like something like u at infinity quantity squared over L. Now L is some arbitrary length scale. We haven't decided what it is yet. U at infinity is the characteristic velocity here on the left-hand side. Because as that goes to 0, of course, all of the rest of the flow disappears with it. Right? So everything is kind of set by this. And look, this wing has a characteristic length. So that's kind of already built in. And if we compare these two quantities, that gives us a sense for how large this term is going to feel. Right? Okay. Let's do the same here. And then, by the way, we can say that this is of order. You've heard that terminology before. O with the parentheses. So we said this is of order u squared over L. And from that, we can sort of look at the viscous stress term. So this one here is what? What's the rough dimensions? We're gonna do the same thing that we did here to this. Okay, we got one of these u's became u infinity, the other u became u infinity squared, and the dx became L. So if we want to do that to the viscous terms, what's the first thing we get for free?
You.
The mu. Okay, the mu, that's obviously going to set some characteristics of the right flow itself. You got to know what nu is. We're going to assume that it's constant in the fluid. That's a good assumption. Okay, now what do we get?
A big game. Maybe U infinity.
Yeah, right. It's still u infinity. It's still that characteristic speed. So we're gonna bring that down. That's u infinity. But now we need to be a little careful here. What is the length scale that viscous terms carry?
It's like a portion of L. Cause it's considering that X right there.
What?
The
Well, this
what's
thing.
perpendicular to.
I mean, yeah, this is always gonna be perpendicular to the main. X is a long wing, Y is upwing. Let's take a step back. Let's have first a look at the advective term. The advective term really thinks about the flow, which is being advected, which is moving. Okay. And here the flow is moving over the scale of the wing. That's how we come up with this sort of dimensionless quantity. It's not dimensionless, right? But if we divide it by this, it would make this first term dimensionless. It's about pulling out the most important factors so we can compare those factors across each of the terms. For the viscous term, do we care about this length?
Delta.
It's about delta. It's about how big does this transition appear? Right? Okay. So in fact, we can do it like this. Right? Okay. Now we can get a little tricky. Okay. So even before we think about the mathematics of delta, we can say that the advective and the viscous terms need to be about the same order of magnitude within the boundary layer. Okay, in this region. Out here, it's clear that the advective terms, they dominate. Because otherwise the flow itself would not appear normal. Right? The reason that the advective terms are at all different is because in this region, the stress terms, the viscous terms, they are of the same order of magnitude. Right? So in fact, we can say something like delta is the square root of mu L over u infinity. Oops, that's a bad infinity, that looks like an 8. Or you can say something like delta over L is 1 over the square root of the Reynolds number. Okay. And then we're going to talk in detail about what the Reynolds number really looks like and feels like. But this is really what it's relating to, is I want you to have a look at the fact that delta is the important length scale for viscous terms, and the L, the wing itself, the wing length, is the important scale for the horizontal velocity components. So really, we could talk about this in the context of something like d dx kind of goes like 1/L. And d dy kind of goes like you'd think it was 1/L. Let's go back to this statement, right? This is the comparison then between L, which is the horizontal scale that matters, and what is delta? What? Well, no, this is, remember, this boundary layer width.
Delta's the vertical.
Vertical. So when I think of ddy, I should really be thinking of delta. What is the variation with respect to changes along delta, right? Is that what you said? Oh. Then I misunderstood you completely, my bad. It's early, it's morning. And also my hearing's not good, old man ears. Okay. So therefore we can take this flow and I'm gonna actually. I know. It's okay. I'm gonna take this and I'm gonna turn it into a dimensionless set of quantities here. I'm gonna take x prime. That's gonna be x divided by L. I'm gonna take y, and it's gonna be y divided by delta. Good. But if I use that definition that I just constructed for delta, then it's really like y divided by L times the Reynolds number to the square root. Okay, I'm gonna take something like u star. Okay, that's gonna be u divided by the characteristic velocity and u at infinity. V star is going to be v, and I'm gonna pull the same trick that I just did. U infinity times the square root of RE. Okay, and then finally P star is P minus P at infinity. Okay, divided by rho U infinity squared. Whew. Now, why would I do that? That seems like such a nuisance, right? What's the point of rewriting all this? Garbage, gibberish.
Trying to see how they compare.
Trying to see how they compare. And also, once you create this system of equations, so remember what the necessary conditions were. We've only asked in this situation for there to be irrotational flow. Viscosity exists, but we're in a steady state. Okay, so the only approximations that we've made here, we don't have the full Navier-Stokes equations, but we do have two approximations in steady state and it's a rotation. And now, if I can write these equations in terms of the Reynolds number, we can take advantage of the similarity solutions. Which means that if I can show flow around a wing that is, very low speeds in a wind tunnel, I can scale that up to any size plane anywhere that I want by simply adjusting those parameters of the Reynolds number, and I'll get the same flow in practice, right? So in fact, we can rewrite these. I'm going to rewrite the momentum equation here. U star, U star, dx star. I know this is going to get annoying very quickly, but it's fine. dv star, du star. dy star, okay, is equal to minus dp star dx star plus 1 over the Reynolds number d squared dx star squared u star plus del squared del y star squared u star. Okay. And you can write something very similar for the v component. But the beauty here, right, is that when we start looking at these dimensionless equations, we can see the importance of the Reynolds number. So if the Reynolds number is very, very big, what does that do to these equations?
Takes away
Takes away what?
the one that's next to the.
Yeah, this one, right, is immediately squished. The bigger that the Reynolds number gets, the smaller this term becomes in comparison to these other terms. Right? And similarly, if I were to write this down, right? Let me write this down now for the V components, the vertical velocity components. So they start out with this. Okay, and it's going to be u star dv star dx star, right? Plus, you get that part. And then the next one is the minus dp star dy star. Okay. Plus 1 over the Reynolds number squared d squared, oops, v star dx star squared plus 1 over the Reynolds number d squared v star over d squared. Whoa. Okay. Yeah, that's supposed to be a star. Just imagine it's a star. Sometimes talky writing no good. Okay. So this is interesting, right? So the y components, compared to the x components, they depend much more strongly on the Reynolds number. Right? And here they're moderated even in this case, right? So this one, the the horizontal gradient of the vertical component is moderated by an RE squared, right? So again, just like it was in the x direction, the most important direction here, or the most important term that is going to be squashed by the Reynolds number is the one that's RE squared. And then these two are of the same order. And of course, it's this one here, the pressure that's being set up that is going to shape a lot of the fluid flow itself. Okay. And as the Reynolds number gets really, really big, okay, this thing goes to 0. This thing definitely goes to 0. And even this whole advective term goes to 0. Right? So if RE heads to 0, heads to infinity, what do you get? Well, you get the continuity equation. That one we're not unexpected. I'm going to drop all the stars. That's okay. Just to make my life a little bit easier. du dx plus dv dy equals 0. You're also going to get u du dx plus u d u d. Got the dot product here, right? Because that's this term plus this, not this one, and this one. right? And then finally, the very last term is that minus dp dy equals 0. Okay. What does the last term say? What is the last equation I wrote?
The gradient of the pressure of Y is like, there isn't one.
Okay, what does that mean? Another way of saying that so that you could explain it.
But not only happened if the viscosity was really big. I think the Reynolds, the pressure just gets affected.
Say that again. Pressure is subsided. What do you mean subsided?
Like, doesn't get taken out, but.
Right. So I'd like sort of where that is headed. Maybe not exactly that word. I would say that pressure is constant. Right. And what that means is like we don't have to care about the vertical pressure gradient. Right. That's kind of what we're thinking about. That vertically, the pressures in the boundary layer must be the same. Right. That's what the third statement says. So within that boundary layer, the pressure vertically is the same. Right? So that means the pressure at the surface of the wing is equal to the pressure at the edge of the boundary layer. That's the necessary requirement, right? So that means that you can find it if you know the pressure from the transition at the boundary layer. Oh, I should bring the picture back up. It'll be easier, right? Okay. Can you see through this or do you want to pull it down? Okay. So out here, in the region in which you don't really imagine, far away from the wing, you find a transition in pressure, right? And if you can find it down to this boundary layer, then you found it all the way to the bottom, right? So you're necessarily getting that through a combination of understanding that these flows can fit one on top of the other, and that all we have to do is we just have to get them to transition smoothly from one region to the next. So above the boundary layer, outside of the boundary layer, we're treating it like an ideal flow, right? Something that is not in contact with any viscous object, and then only have to deal with viscosity in that delta. And this is the power of boundary layer dynamics. Okay, outside of the boundary layer, no viscosity. Inside of the boundary layer, where the object is interacting with, a solid thing interacting with the fluid, it creates problems and it changes the flow and everything else. But it only does it in a little region. Cool, right? Comments, questions, concerns? This is how we think about boundary layer thickness. Let me bring this down.
So in a real world scenario, when the negative dq over dy is equal to 0, for the equation to show as lift would have to equal a negative number. Because of negative pressure on top to get the lift, or how would that look like?
Yeah, so we need to not think about that, right? Because that is not how planes fly. So we think about it as being pressed up, right? But around the boundary layer, right? The transition is so okay, what I mean by this is the flow on the top, the flow on the bottom, right? And you traditionally have thought about the fact, well, if you have some object like this, and it's flat on the bottom and the flow takes farther to get up, then as it goes up, according to the continuity equation, it must move faster, and so therefore the pressure above must be lower than the pressure below, and therefore it pushes it up. Right? Well, what did I just show you with the boundary layer? I said that after you exit the boundary layer, you head back towards normal. Right? So there only is a very small region in which that's happening. And yes, it's true that the pressure out there must be lower, right? So it's this pressure that's right above, and then there's a vertical, just constant pressure down to the surface. So there still is a pressure difference, but it's not exactly from the same way, right?
So it's more related to like a butter knife going through butter, because
Well, I'm not sure I want to use that analogy, mostly because I don't understand it. And second, because the physics is like a solid going through another solid,
okay,
right? So even though it's cutting through this object, right, the dynamics there, far away from the wing, right? So the only thing that I want to caution us against is just thinking that the Bernoulli method of changing the flow, right? When we do Bernoulli through a tube, or we do Bernoulli in undergraduate at the very beginning of our physics careers, we think that it affects all fluid everywhere. And that's certainly not the case. Because as you move away, you saw from this previous example, okay, yes, it changes the fluid here, but here it overcompensates, right? It's going faster, so the pressure might be lower here. We haven't yet proven that, right? But then what do we think is happening here? Do we not also similarly expect that the flow down here is going to have some boundary layer that has a faster amount because it's still moving out of the way? Right? And then this is usually where people say, well, wing shape, wing shape. And we'll talk about wing shape in a little bit. Wing shape, of course, is very important. Because the wing shape itself, not just for the fact that, oh, it's having a longer path, that's, I think, too rudimentary an explanation, but more importantly, how does the boundary layer affect the vertical distribution of both pressure and, of course, velocity? Right? So we see something like this, and of course, this is still a symmetric wing. This is two symmetric wings fly.
Do switch ones, well.
Guess we'll find out. We'll go and fly them today. Okay. And I want to show you here, we were talking about this boundary layer, and I just showed you at one place, right? So I just showed you here, I showed you the vertical velocity, and I said, well, the boundary layer thickness changes, right? It's very small over here, very big over here, right? And that is fully going to be representative of the fact that you have a transition. Here, the transition is going from zero velocity to fast velocity quickly. As I move down the wing, I can create a larger boundary region because I have more air or fluid, what have you, that's sort of standing off, right? And so that transition can go much more slowly, and this delta can be much wider. This is a whole section that I'm definitely not going to have time to get into. Go into chapter 10.2 about boundary layer thickness. It's really fun. But excuse me. One thing that I'm going to show you some really fun pictures today. But I just want you to be thinking about the fact that the boundary layer here, this is upstream from the flow, and this is downstream from the flow. And what we have here is momentum transfer, but it only happens downstream. So you have sort of the breaking of the time symmetry of these Navier-Stokes relationships. So even though the thing is in quote unquote steady state, there's clearly an arrow of time here, right? Because the flow, if you reverse to minus u, right, and you just imagine time going backwards, it wouldn't quite make sense for the flow to go in towards the object here, right? Okay. Let's see what else I want to say here that's important. There's some fun solutions, for example, 10.3, 10.4. These are all different ways of dealing with your boundary layer mathematics. But I'm going to go ahead and show you one of my favorite fluid dynamics pictures of all time. Go away. Come on now. Oops. Got ahead of myself. It's not this picture, although this is a cool picture. Talk about it. That's Aurora, but it's an example of a fluid interacting with the ones that we're talking about. Okay, so we talked about that, right? Okay. This is, I think, the when you think about the importance of something like the Reynolds number, or you think about the relative contributions of the advective term to the viscous terms, this is what we're thinking about. And you may be thinking in your head, well, why isn't it the case that for a Reynolds number of 1, why isn't it the case that for a Reynolds number of 1, shouldn't that be where these terms sort of match? And then anything that's different from 1 is one term being more dominant than the other? Well, that's not always exactly the case, because as we saw here with the flow, right? The Reynolds number, which is down here, is acting like, I could flip this around. If I rewrite this term here, I would square this and I would flip them. So the Reynolds number would be something like L squared over delta squared. Right? So what is that really doing? Well, it's looking at a comparison of these lengths. Right? And in which cases is the boundary layer comparable to the layers, the largest layers of the object that I'm looking at, right? Because those advective terms here, the ddx's, they look bigger than the ddy's, right? There's smaller variations in the ddy's. And sometimes, of course, this is the ddx versus ddy. This might have a big U, the U at infinity. The advective term might be much larger than some vertical velocities that might occur because of viscous terms. So here, we start on the left-hand side of this equation with the Reynolds number approximately equal to 1. And that just says that this is sort of the boundary layer here. And this is the vertical height of the boundary layer. And out here, you have laminar flow, completely laminar, doesn't even know that there's a boundary. This is the surface. So this is something that is not moving, and the flow is moving to the right. Okay? And I want you to see the sort of shape, and I'm going to put this in quotations. This is a diagram, right? This is as scientific as the scribbles that you see on the right-hand side. You see how the shape of this boundary layer grows with increasing Reynolds number. Now, how do you increase the Reynolds number? Well, you can do that in one of two ways, right? You can think about it in the way that we've written the Reynolds number before, which takes into account the relationship of the velocity and the viscosity and the lengths, or you can think about them in the terms of the boundary layer width versus the scale of interest, right? And so here, you start off with sort of what we just had. Some smooth transition down to, 0. And you'll notice that those answers, they're already with Reynolds number greater than 1. Much, much greater than 1, right? These are the laminar boundary layer equations. When the Reynolds number is massive. Okay? You transition here, okay, at this Reynolds number of 10 to the 6, okay? This is the first occurrence of what we call Groth's disturbance. So when you have some disturbance, some variability in the flow, that turns into larger variations as opposed to settling out or dissipating. Right? Because the viscous terms are really good early on at taking flow and just having them sort of diffuse out into the flow, right? At this point here, you have this similarity region where the initial conditions basically forgotten. Doesn't really matter what you started with. You're gonna end up very similarly. And then here you have this disturbances. And so we call this like XT. You basically take some two different fluid dynamics choices and you simulate them or you model them, you create path lines, whatever, and you watch for how do they diverge. Because if you're watching this guy and you're watching this guy and they start very close to each other and yet they end up very far from each other, you may be entering a region of what we call instability. Because of course, in a laminar flow, we expect two layers, parallel layers, to end up pretty close to each other, right? That's the definition of laminar flow. So it's this region near 10 to the 6 that you finally start to see them varying. Okay? And then finally, you keep getting RE even larger and larger, and the flow becomes increasingly irregular downstream. And this is where you start getting these weird kinks and these spirals and these eddies until you diverge into full-blown turbulence. Okay? Questions about this? Okay. You've stuck rocks into streams. Okay. You'll have sort of picture in your mind of what happens when you do that. Can you describe it with physics now? Rock stream. Good. Okay, so let's think about that in detail, right? Let's take the flow, let's bring it this way. My hand is the rock. Stream. Okay. Let's think about the boundary layer here. And we're gonna do only one thing to the boundary layer. So we could vary the rock, we could change the fluid, let's not do any of those. Okay. Only thing that we want to change here is how fast is the stream. Go. Okay. So let's make it simple. Let's make a circular rock. Everyone loves circular rock. Circular rock, big flow. So imagine there's no edges to the stream, and it's just going around the rock. Okay, obviously you cannot go through the rock. So how does the velocity at the rock surface go? That's 0. Good. So I want you to just sketch for me, okay, what the picture is of the flow near or around this rock. Yeah, show me a rock. Okay, okay. I like that. So it just gets out the way.
Oh, you want it all the way around too?
Well, yeah. I want to see what happens downstream.
Like a top view side view.
Okay, okay. All right. Okay. Okay, so I see a lot of like flow being diverted around the stream and then kind of going back to normal. Is that right? Okay. What happens if you make the flow go faster?
Your boundary layer is gonna be bigger.
Which is going to be bigger. Okay, so it's going to change in some way. And does the flow go back to normal?
Maybe after a longer distance.
Right, because we said that the boundary layer usually takes the momentum and it creates disturbances downstream. Right, so you're saying, okay, well, maybe you just gotta wait a little bit longer. Maybe it creates some envelope, and that envelope keeps getting dragged downstream. Right? Okay, so let's have a look at what happens when we do this in the lab. On the left-hand side, you have a Reynolds number less than 4. Now, this is not a simulation. This is you take a circle, you put it in a lab, you put fluid around it. So they're just watching, right? All they're doing is they're just turning a knob. It's not a Reynolds number knob, but you get the idea. And they say for experiments where it looks like this, you get this really weird thing, right? It looks like the streamline just fucking stops, which is crazy. And this thing does, I think, what all of your pictures do. It kind of goes around and stops. So that is sort of the simplest case, maybe the lowest flow velocity. As you start to ramp it up a little bit between 4 and 40, you get these little things, right? There's clearly you've broken the left-right symmetry, okay? Now you know which direction the flow is coming in, even if I didn't put these little arrows, because you would never get these little lumps on the leading side. You would only get them on the trailing side. And you get these weird little lumps. They look like, you have some flow that's heading back, and they're creating these sort of counter currents. These little rotating, and of course you've seen this if you've seen a rock, you can kind of throw your leaf behind the rock, and it gets trapped behind the pool. Right, so maybe you've ever played this game when you were a kid, there's like a stream, and everyone has their leaf, and you try to race them downhill. Like, fuck, mine got stuck behind a rock. That's why. Right? You get stuck in these turbulent eddies that occur behind the rocks. Now, I shouldn't say turbulent eddies because we haven't quite got there, but you have some form of a vortex, right? Something that's rotating. Okay, and then you get this really cool one. Right? And between 80 and 200 Reynolds number, you get something that looks like maybe you were doodling it in high school. Right? Like,
That's sort of roasting.
what?
That's sort of roasting.
Yeah. So are these real? Yes? Have you seen them before in your life? What?
I think.
Well, they don't, I mean, so like, I've never seen this in a rock and a stream, right? That's kind of a weird thing to see. So this is like very like, I've seen this. I don't know about the first thing. We're gonna come back to this. This is a really cool one. You do see this, but we have to be a little careful in how we interpret this one. Usually you get something like this. There's a transition between this one, and we don't tend to see this in the middle unless you get really lucky. It's a very small region of Reynolds space. Okay. In this region, you get what we call turbulent wake, but a laminar boundary layer. So you set up the physics such that the turbulence only occurs behind here in this object. And you still have the boundary layer, which is a series of parallel layers. Okay. And that's for Reynolds numbers 3 times 10 to the 5. Larger than 3 times 10 to the 5, you actually get a turbulent boundary layer, where you have little vortices, rotational cells that are occurring in contact with the object. So not only do you have a boundary layer that extends out, creates its distance delta, it's turbulent in here and it's turbulent in the turbulent.
Where's the angle say?
That's the angle from which we have what we call separation. So what I mean by that is, okay, here you have the stream function, or you have the streamlines heading in. They sort of contact this object. Okay.
180?
What?
Is it like from the left to the right? So that won't be like 180 as David wrote it?
Well, this one hasn't separated yet. The separation occurs here because you have this laminar boundary layer, right? And you see how this streamline comes off underneath, right? And similarly here, this streamline emanates underneath the turbulent boundary layer. So we call this separation of the boundary layer. Let's see, what do they call it in here? Yeah, separates. They say, there's a forward separation point, which is here. There's a distance between the forward separation and sort of the backward separation of these streamlines. There's a cool picture in 10.19 of a von Karman vortex stream at Reynolds number 55. It looks like this. This is a simulation, obviously not a picture, but this is a simulation. You could even make your flow do this good, right? In order to do this on a computer, you just have to model all of these data points. You got to invect them. You got to have a boundary layer. And then you'll notice that as the flow goes over, you're seeing all of the phenomena that we were talking about before. So I wish I could pause this. Damn it. Can I pause this? Damn it. Okay. Well, as you watch, just pay attention just to this color, this darker color. And you'll notice that it sends back some flow behind, and then it wiggles back and forth, back and forth. And as it does that, it launches these little circles downstream, right? And this does happen in practice. You see them?
Are they hitting a mountain there? Or what's that black thing in there?
Yeah, that's exactly what that is. This is an island. So this is an ocean, and the flow here is the air. The air is moving to the right. And what you see is some, either relatively circular mountain or whatever. It creates a boundary layer in the air itself. And the flow is such that you create these circling cloud features. And notice that they're all spiraling in the opposite directions, right? So the ones here on the bottom, they are spiraling in. The ones on the top, sorry, I should say it differently. The ones on the top are spiraling clockwise, and the ones on the bottom are spiraling counterclockwise. And we can see here, that was the same thing from before, right? These dark ones, they're spiraling clockwise, and hence that's how you separate the rotational velocity of the two, right? Whereas when you see it here, it's actually, you can kind of see it better on my computer than you can see it here. It's not showing up super well. But this is a mouse. This is like an island. And it's big. You just can't see the tip. This possible. It's crazy.
That looks so similar to like the Tesla valve. Like in the shape of them.
What do you mean the Tesla valve?
Tesla made up his own valve, and it kind of follows like that similar pattern.
Oh yeah, yeah. Yeah, this one is it's a von Karman vortex. If you want to look that up. They occur in nature a lot. And this one, I forget exactly what the Reynolds number in which it's occurring. There's another example in 10.21 where they have, let's see how fast that flow is going. No, they don't say. Okay, so this is fun. Let's talk about typical values of Reynolds numbers. Okay. These are objects, right? And we're thinking about them in the context not just like bacterium. Well, bacterium is certainly not a fluid, right? But you want to think about it in the context of what do bacteria normally exist in. So they're in some fluid, they have a length scale, they're moving around with characteristic velocity. Their bacterium 10 to the -4 Reynolds number. How do we interpret that? What kind of world are they living in?
Microscopic.
Yes, of course they're living in a microscopic world. But do they live in a world like you and I live? Do they live on a solid land? No, they are in fact. What? Yeah, they live in the fluids, right? They're fishes, right? They're swimming around. What kind of swimming are they doing? They're swimming in laminar flows. Super, super laminar flows, right? They are small enough, of course, real small dudes, but they're still in fluids. right? They're not so small that they're bumping into the individual molecules. They still see the molecules themselves as aggregates of the whole thing, kind of like we do now. Okay? And similarly, ciliates. Okay, this is a smaller type of cell as well. Also 10 to the -1. Smallest fish. This is the smallest fish you can think of. A goldfish? Goldfish are big.
Okay.
What?
Oh, is it those? Whale? Oh, sorry.
Krill?
Oh, krill,
Minnow.
this,
Minnows are good. Minnows are really small. Yeah, I would go. I mean, maybe anchovies. Anchovies are quite small. Okay, that's fine. Smallest fish. One. So there's boundary layers around them, right? They're still mostly living in a quite a laminar world. Most of the time, you don't find the smallest fish in the most turbulent of places, right? So what are they gonna do if they're in a wave? Like it fucking works, right? They're tiny. Blood flow in the brain, turbulent or laminar? So now I have two people with two different words. Which one? Let's go back. Yes, that's a great question. When does turbulence set in? Because our instincts, we as physicists and not as necessarily fluid dynamicists, right? So fluid dynamics is not typically taught to physics students, it's taught to like engineering students, right? And physicists, we say, well, so if one number is bigger than the other number, then that must be this, right? Reynolds number is a little fucked, right? It's clearly designed by someone who wasn't thinking about how we would use these dimensions of numbers in the beginning. Because I would love for Reynolds number bigger than 1 to simply be turbulent. But in fact, that's not where the transition occurs. The transition occurs at
much greater.
yeah, much greater. Let's go back.
Is it a scale different for every, I don't wanna say for every fluid, but it's just strictly Reynolds number, huh?
What do you mean?
Cause this, like you see how it says 10 to the 6?
Yeah.
Oh, it's dimensionless, right?
It's dimensionless, right? But okay, so hold on. So let's be a little clear, right? So it is dimensionless, but it's also for this specific type of interaction. So here I have the plate moving to the right, or maybe it's solid and the flow is moving past it, right? Now that tends to do most of all of our boundaries, but not necessarily every single one, right? So the ball is not exactly like the ball with the flow moving past it is not exactly a flat wall. And the transition into turbulence is not going to be exactly the same location. So for every fluid, for every flow, they kind of vary. But generally speaking, as long as you get the geometry right, then the physics with respect to the Reynolds number will be the same. So if it's the same geometry, the same Reynolds number, that is fine to compare. But if you have different geometries, we can't necessarily compare the Reynolds number 1 to 1. However, it's not as though moving from a circle with flow moving past it to a wall, that doesn't change the Reynolds numbers from 10 to the 6 down to 10 to the 2, right? It's very small changes. And so in fact, when we look here at the typical Reynolds number, you see that the blood flow in the brain of 10 to the -2, that 10 to the 2, so 100, that is laminar flow. Okay? And it's actually really good that it's laminar flow, especially blood flow in the aorta. Now, blood flow in the aorta is more than blood flow in the brain. Why is that?
The bigger vein or a bigger.
Yeah, it's got a big old hole, right? And it's getting pumped in there, right? So one of the things that we have to remember about how our brain works, right? We gotta pump it up. Pump up the jams, right? Okay, as it goes, I just had to. I didn't even hear myself do it. I didn't need to, but I heard it, I had to do it. Don't come at me. Okay, so the blood flow in the brain, you have to get it from the heart all the way up, right? And you know, of course, that if you lose blood flow to the brain, not good. So you want it to get up there. You want it to be moving, not necessarily super quickly. It doesn't have to be moving light speed, but it needs to get enough oxygen up there. And usually it has to go down through the lungs, oxygenate, and then back up into the brain, right? So where is it doing the pushing? Well, it does the pushing in the aorta. This is where your blood's moving the fastest, right? Because even though you have gravity to assist you as it falls down, your body just says, well, if it's headed down there anyway, I'll just let it go, right? I'm just gonna suck what comes back up, right? And that's what the pumping does, is it pulls the blood up from your toes as opposed to pushing it down towards you. Pushes up your brain, lets it fall back down, right? So these both prelaminar, right? 10 to the minus or 10 to the 3 prelaminar. You start to get into turbulent flow. Okay, when you get to somewhere between little over 10 to the 3 to 10 to the 4 for pipe flow, 10 to the 6 for any sort of like a ball in a thing, right? So that was the 10 to the 6 was the boundary we saw for the wall, right? And then for pipe flow, which would be like blood vessels, it can be actually quite small. We talked a little bit at the beginning, I don't know if it was the beginning of this month or earlier, we were talking about why would it be good or bad to have blood flow that is turbulent? Right? And I gave you two hypothetical situations. I said, well, turbulent, it helps to like, you start with the oxygen and you're like mixing it up, right? And so that like distributes the oxygen better.
Oh, yeah. You wanna answer now? Supposed to think about it.
Yeah, why would you thought about it the whole time, right? You went home and you worked on it.
I'm gonna guess if it starts to look like what you're showing us, that's bad, cause it's clumped up now.
Okay, that's one way of thinking about it, right? It's bad because it's clumped up. Now, another thing that I might say, right? Let's see if we go back here. You have some fluid flow, right? And you feel these effects downstream. So what that means is that there is some time irreversibility to the physics, right? So you can only see the physics going in one direction now. What does that mean for the energy in the system?
It's dissipated in the turbulence.
It's dissipated in the turbulence. And that's really important to remember, that turbulent flow takes more energy out of the system. So for the same, let's say you pump your heart and you're trying to push it through some valve. Let's say the valve is like partially blocked. And that ramps up the speed a ton. Okay? And then after it ramps it up, there's still viscosity in there, right? And you get all of this, like, let's say you get a bunch of turbulence behind. Then you dissipate that kinetic energy into either heat or friction with the surfaces, right? And it's not like it's warming up your blood and boiling it, so you still get rid of that heat. But now the ability to push past that blockage goes down. And your fluid flow goes down, right? And we don't like that because that's how you die. That's how you get a brain aneurysm, right? So here we want to think about the blood flow in the body and the blood flow in the brain and the aorta as being well below this, 2.3 times 10 to the minus 3 onset for turbulent flow. And we think about, of course, bodies are designed by natural selection. So if your body happened to go above this, it would be inefficient. So it's kind of interesting that your body naturally sort of approaches this actual physical limitation without surpassing. Cool, right? If you like baseball, yeah, baseball. You can get a baseball to move. And so as you throw the base, I should have brought the baseball. Of all the times to not bring the baseball. I bring the baseball because what is the shape of a baseball? Round. Good, okay. Ball, Chris Lonnie, don't be stupid. Spherical, is it exactly wrong? No, why not? What? Is stitching, right? There's stitching on it. Yeah, I mean, you're right. That's I'm describing the shape, but like, what is it about? There's stitching on it. If I threw a perfectly round baseball, could I throw a curveball?
Oh, no.
No, I couldn't. What happened when FIFA took the soccer ball and decided to take out all the seams? Everyone hated it because it went in unpredictable way. You couldn't bend it like Beckham, right? And the shape of the object creates, so let's start with a spherical object, right? Uniform boundary there. Okay. Now add a seam. I add a seam laid across it like this. Okay. Now there's vertical and horizontal variations in the boundary. And if there's vertical and horizontal variations in the boundary layer, then as I spin the object, for example, with a baseball, if I'm spinning it in one direction, I'm creating a difference in the boundary layer on one side versus the other. And if, for example, I rotate it just like this, okay, and I create on one side flow that's moving faster than on the other, kind of like how we talked about with a plane wing, you can get that difference in the rotation. No, it's a little different than just the simple explanation because you want to take into it something called the Magnus effect from the rotating object. But what you can do is you can get it to move to the left. So while you throw it straight, it can dip down into the left. Or if you're throwing it straight, but you rotate the ball in a specific way, you can get it to go like this. Right? So I'll show that again, like this, right? And that can be called a slider, sweeper, a curveball. They literally design all of these things in the lab after watching how the ball flies. Okay? And a typical pitch in Major League Baseball, about 10 to the 5, that's just about after turbulent flow starts to set in. So what folks really care about in these pitching labs is something called wake shifted or seam shifted wake. And essentially what that does is as the ball is rotating, flying through the air, it creates a little bubble around it, right? And the question is can you use that bubble of air to give late motion to your pitches? Because if you can get that ball to appear to be going down and then at the last minute turn left, right? That's fucked, right? So what they want to do is they want to think about how we can utilize turbulence around the boundary layer in order to divert the flow of the ball, right? Because to the ball, the air is just moving by it, right? So typical pitches, they happen right in that transition to turbulence, and they take advantage of the transition to turbulence.
We ever played blue baseball?
What?
That's literally what it does. It looks straight and then like I don't know where else.
Yeah. Yeah.
They tried.
They tried. Well, we baseball not famously known for their physics. Okay, people swimming, fish swimming, turbulent. Turbulent, right? Turbulent as fuck. So that's Michael Phelps, and you can see that in the water, right? Even when they're going, why do you see that in the water? What do you see? Like even when they're fully underwater, how can you see that it's turbulent?
Surface just
Even fully under the water.
Air bubbles they create.
Air bubbles they create, right? So as they're swimming, even under the water, and you can see this with fishes under the water, as they move their fin or something, right? And you see these little like, and they create bubbles out of nowhere. Right? How do they magic these bubbles?
Oh, so it's like the boundary layer opening and closing as they go through it.
Yeah, I mean you have water inside, right? Sorry, you have water. You have air trapped inside. You have air that's potentially on their bodies, right? You have all of these things in contact with one another. You create these little vortices, and you can just get streams of bubbles. right? If you think about, has everyone here drank beer before? Everyone 21? Okay, just make sure, don't have to record anyone. If you pour beer into a glass, or let's do champagne. You pour champagne into a glass, because you can see quite well. And I encourage you to think about this next time that you're looking at champagne poured in the glass. It appears that the bubbles come off of the edge of the glass, no? So look at a glass of champagne. Where's my? Okay, but just listen, let's say you're getting married. Okay, and you're required to have champs.
Relatable.
Okay? You're required to have champs.
Mhm.
Okay, and they pour it in your champ. Like that. Where did the bubbles come from?
It's like from the bottom.
But from where? Okay, again.
Wait.
From why, why don't the bubbles come from here? Like in the fluid.
I can all stay on the side.
But,
You're saying this right
but why?
after-
Why are they coming off of the side?
This is like after you poured it, it's whatever.
Yeah, you pour it in the middle, right? And then watch the fluid. None of the bubbles come from the fluid, they all come from the glass.
Oh, it's a boundary layer in the glass then.
It's a boundary layer in the glass. Now the flow is not moving, obviously, but what's happening here is you are creating a surface on which you can cavitate bubbles. And you cavitate bubbles, you take dissolved carbon dioxide in it, and you give it a place to condense and create a bubble. And you can do something very similar when you create turbulent motion in swimming water. I think that's the explanation. I'll double check that, but I'm like 90% sure that's the explanation. Okay. And then you have blue whales. You've heard of those before? Okay. What's cool about the blue whale aorta?
Swim through it.
You can swim through it! That's sick! Okay. Large ships. Turbulent as fuck, boy. Right? Hurricane. Turbulent as fuck, boy. Right? Okay. If you love baseball and you want to hear more about it, 10.9 talks about cricket ball dynamics. If you don't know what that is, you can just skip to tennis ball dynamics or baseball dynamics, all of which they're dope. And essentially they just use turbulence on one side of the ball than the other to turn it left, right, center. Okay. And you have this really cool picture here where they do like smoke flies past a rotating ball. And you can see that there is turbulent wake that is going to push the ball in various directions. Okay, I would love to spend much more time in this region, but I think that's probably all we're gonna do for boundary layers, right? I think we could spend probably the last class talking about these sort of types of waves, or we can just jump right into instability. Do you have a preference for thinking about more different specific types of internal waves, or do you want to think about instabilities and shocks? Because we haven't really even talked about shocks. Shocks are places where the fluid dynamics equations encounter lack of continuity. And that actually, it doesn't mean that you can't solve the equations. It just means that you have to understand the boundary conditions through the shock. There is discontinuities in the equation and they still work. It's just kind of wild. Shocks over instabilities.
Well, but if you have to do a real.
Well, instabilities are chapter 11. Shocks, I believe, are chapter 16. Let me just double check here.
Geowaves, that would be like earthquakes or nothing like it.
Geowaves are waves that are happening at the scale of the Earth.
Um,
So like Rossby waves and Kelvin waves are gonna be the ones that you see in clouds as one layer of air moves over another. What it'll do is it'll suck up, for example, the cold, cold, wet air. It sucks it up, and then turns it over, and you get these cool like wave shapes in the sky. Internal waves, we've kind of talked in detail about different types of internal waves. This is giving you more examples of how they happen. Rossby waves, these are planetary scale waves that occur when you balance different parts of the Navier-Stokes equation. Ekman layers, this is the way that motion, so we talked about the Coriolis force and how it deflects left-right motion. What happens as you go down? And so Ekman layers we see a lot in the study of the ocean dynamics, specifically the first, 300, 500 meters, and how flow near the top leads to sort of twisting down into the ocean. So,
okay.
no, go ahead.
Would Eggman layer touch with eddy currents? Do they touch with that, or is it something else?
No, Ekman layers, they're still layering. It's very laminar type flows. These are all considered sort of laminar solutions. Instabilities, right? So this is when we would talk about something like the Kelvin-Helmholtz instability. The Kelvin-Helmholtz instability is a famous instability by which you have something hot under something cold. And famously, it doesn't want to have that, right? Especially if you have gravity pointing down. And so how does it go about reorienting itself? Instability just means that you set the situation up that it doesn't want to be in there. And how does the physics reorient itself? You have sort of compressible flow, which is, not chapter 16, chapter 15. Compressible flow talks about shock waves. So you get to talk about sort of nozzles, you get to talk about rocket flow, stuff like that, supersonic flow. So if people have a preference, just let me know. We could do aerodynamics, we could talk about lift. We could talk about the lift of specific, like turning airfoil shapes into lift generating objects. Preference. No preference. So I talk about what I want to talk about. Let's go. Okay. Anyone have homeworks for me?